what happens to the covariance terms? These are when I and j are not the same. Exactly. So those terms become 0, and you're just left with the summation of your variance of xi's. So basically, this result says if I have independent random variables, the sum of the variance of the sum of the independent random variables is just the sum of the variances. So that's the formula in general, and then if they're independent, that term drops out and you're only left with the variance. It's just the sum of the individual variances. Okay.
Say that one more time. If they're independent, then the variance is equal to the sum of...
The variance of the sum of the random variables equals the sum of the variances.
Okay.
So variance of the sum equals sum of the variance. So you just add up all the variances. Look at So let's do this example. A really simple example. Let x1, x2, fn be independent and identically distributed random variables. Sometimes I might just write IID, and that means independent and identically distributed. So it means all these random variables, they're independent. Identically distributed means they all have the same distribution. So if I say x1 is normally distributed with mean 5 and variance 2, then x2 is also normally distributed with mean 1 and variance 2. So they all have this, come from the same distribution. And they're independent too. So this is typically the case when I talk about something called random sampling. So when and this is getting into some statistics. So in statistics, what you want to do is, if you want to get some information about the distribution, say you want to know about the distribution of heights of people in a certain population, the way you do it is you draw a sample from that population, right? So if you think that it's normally distributed, theoretically speaking, we have a random sample before you actually draw the sample. If you draw the sample, you actually have values. But before you draw the sample, you know that if you draw a sample of size n, your first value that you pick, you don't yet know what it's going to be, but that you know is going to have, you're picking it from a normal distribution, so x1 should be normally distributed with whatever mean and variance that distribution has. And then I can sample again a second time independently. So typically, if the sampling is done right, we assume it's done independently. So you can talk about x1, x2, xn denotes what's called a random sample. So in random sampling, you get n IID random variables, okay, coming from that distribution. Alright, so if I say x1, x2, xn is a random sample, I basically mean it's independent and identically distributed. So if they're independent and identically distributed with mean mu and variance sigma square, find expected value of x bar, and I'll tell you what x bar is, and variance of x bar, where x bar is this new random variable that you define as follows. So that's basically x1 plus x2 plus x. So I have n random variables, I sum them and I divide that by n. So x bar is typically called the mean of the random sample. So if I have a random sample, x1, x2, xn, and I calculate this random variable, so this again is a random variable, right? And
is that true for all distributions or just for normal ones? Well, you have that it's identically distributed, and then you use mean and variance, which would imply normal, right?
no. I mean, for any distribution, every
Okay.
distribution has a mean and a variance, right?
Okay.
Basically it means, and since they're identically distributed, that means they all have the same mean. That is, for all I, and the variance of xi is sigma squared for each of these random variables. They all have the same mean, they all have the same variance. The reason I'm interested in this kind of random variable is because statistically this is a very important kind of variable. If I actually observed values for this random sample, so I actually had a sample, this means I just take the average of all these values. So our capital X bar is random in the sense that with each sample that I draw, supposing I draw, if n is 5, say I draw a sample of 5 first and observe its values, I can calculate the value of x bar. If I take another sample of size 5 and I calculate x bar, it will be a different value. Basically, I see that x bar can take different possible values, right? Okay. So for a random sample, this is a random random variable too, because depending on the values of this, you have your value of x bar. So again, that's a random variable. And I'm interested in what is the expected value of this random variable and what is the variance of this random variable. Okay, and the results are very interesting and useful for statisticians. And will lead us into this idea of in the law of large numbers. All right, so if I have independent identically distributed random variables, each with mean, mu, and variance sigma squared, so I have a random sample. Let's calculate what would the expected value of this random variable be. So we're going to use all our properties that we know and calculate this. So this is expected value of 1 over n, x1 plus x2 plus xn. 1 over n is a constant. What do I know about expectation? I can pull a constant out. So it would be 1 over n, expected value of x1 plus x2. I can use my other property of expectation that says expected value of a sum is just the sum of the expectations. I think it's like the second property I wrote down today. Now, since these all have the same distribution, that means they all have the same mean. So I have mu for this, mu for this, mu for this. That means I've added up mu n times. So basically, if I take a random sample from a distribution with mean mu, and I look at this random variable, x bar, it also has the same mean. as the mean of the distribution from which I've sampled. So it has the same mean as each of these xi's, so that's something interesting. So when I say that xi's have mean mu, it means every time I sample from the distribution of xi, on average I get the value mu. Similarly, for each sample that I take and I calculate x bar for each sample, on average the value that I get for x bar will be mu. Okay? So that's something nice. Okay? The result we get for variance of x bar is even better. So and I'll tell you why. So let's calculate what the variance of x bar is. Variance of 1 over n, summation I equals 1 to n xi. What do I know about variance of a constant times something? When I pull the constant out, I get square, right? 1 over n squared, variance of summation 1 to n xi. I know all my xi's are independent, so I know the variance of the sum is the sum of their individual variances. So I get sum equals 1 to n each of these xi's.
Thank you.
And what else do I know? Each of these xi's have the same variance sigma squared. I just use sigma squared to denote the variance of each of these random variables. And so I add this constant sigma squared n times. So I get n sigma squared over n squared. Sigma squared over n. So I've got the variance of this random variable x bar is sigma squared over n. So why did I say that this is good news, that variance of x bar is sigma squared over n? As n gets larger, it means we're taking a larger sample, right? The variance then gets smaller. Okay. So if I take a larger sample, the variance is smaller. The variance means if I sample many times, on average, if I calculate x bar for each of these samples, on average, I get the value mu. The deviation in these calculations will not be too large because I know the variance of x bar is sigma squared over n. The larger sample size I take, supposing I take, each time I sample, I take a sample size of 100, then the variance of x bar is now reduced to sigma squared over 100. Okay? So the larger the sample size I take, the less variation I have in the value of x bar. Okay? So supposing I calculate, I take 100 samples once, then I do the experiment again with another 100 samples. If I do this experiment 5 times with 100 samples, and I calculate x bar for each of these samples, I get values very close to mu. Okay? And I get them pretty close to mu because I know the variance in my x bar cannot be too large. So that's useful in statistics because it tells us that calculating x bar gives you a good estimate for the mean of the distribution. So supposing if I didn't know what the average heights of people were, what I should do is take large samples and calculate just the average value. Just add up the heights of each person in that sample and divide by n. And that would give me a value pretty close to the mean height of the population, just from a sample. Clearly, the larger the sample I take, the better this estimate is because there's less deviation from its mean. So the values of x bar get concentrated around the actual true mean of the distribution. So this information that the mean of x bar is mu and the variance is sigma squared over n tells us that random sampling, if you calculate x bar, it gives you a good estimate for mean. The larger the sample size n is, the better an estimate it is. All right. right, there are two more comments I'd like to make. I'd like to define this last term there, correlation.
So, when it comes to covariance, the actual value that we get is not important. It's just the sign.
Yeah, in a sense, yeah, it's basically the sign that's important. Basically, if it's plus, that means the covariates are together in the same direction, and negative covariant in the opposite direction. Yeah. So if you're trying to make some deductions from the value of covariance, it's basically the sign that tells you, that gives you information. But now we have correlation, and in correlation, the value also matters. So correlation is basically you take covariance and you scale it by something. And so let me define that. Correlation of two random variables, x and y, which is denoted by rho of xy, so that's the symbol rho, is defined as long as there is x and there is y is greater than 0. And it's defined by, so we only talk about correlation when x and y are not constant. So if variance is 0, it means your random variables are constant. So if they're not constant, we can talk about correlation, random variables, and that's defined as this deviation. So correlation is just the covariance divided by the standard deviation of x and the standard deviation of y. Some remarks about correlation, we will not prove these, so it's just, I'm just going to state them, is that your correlation is always a number between x and y. I mean, it's always a number between x and y, between -1 and +1. So scaling this ensures that correlation ends up being a number between -1 and +1. Now, here's where the value of rho also matters. Of course, in the case of independence, covariance is 0, so rho is 0, that's fine. Now, if correlation, okay, so maybe I'll put this as a remark. Correlation is a measure of the linear relationship between x and y. So it's not just a measure of a relationship between them, but how they're related, how linearly they are related. Okay? So if y was just a plus bx, so then they're perfectly linearly related, right? Y is a linear relation of x. So in this case, rho is +1 or -1. Then rho is equal to +1 -1. So the absolute value of rho takes a larger value depending on how linearly they are related. So if there's a perfect linear relation, rho is +1 or -1. When is it -1? To -1 if the slope is negative, clearly. So this means as x increases, y decreases, basically. So it's a line like this. So then rho is negative. It's -1 in fact. -1. If the relation between x and y is linear and the slope is positive, then rho equals +1. So b is the slope. So clearly then you see as x increases, y also increases, so the covariance is clearly positive. And so the correlation is positive. It's exactly 1, and it's exactly -1 in this case because there's a linear relation. And I think this is obvious, but I'm saying that if x and y are independent, then the correlation, because the covariance is 0. Now there's one important remark that I'd like to make, which is about covariance as well as correlation. So I've said that if x and y are independent, then covariance is definitely 0, right? But if covariance is 0, it does not mean that x and y are independent. It can just mean that they're maybe not linearly related. Say if y was a plus bx plus cx squared, they're not exactly linearly related, but there's some amount of linear relationship between them, right? So your rho may not be 0 here, but it will not be +1 or -1. So rho is +1 or -1 only when y is a linear function of x. In this case, rho would be something between, would be something less than +1 and greater than -1. So here the remark is if covariance of xy equals 0, okay, so let me say covariance of xy need not imply x and y are independent. So this is a very important fact. So it's wrong to conclude that if you calculate your covariance and you get 0, that x and y are independent. So it only goes in one direction. If x and y are independent, covariance is 0. But covariance is 0 does not mean x and y are independent, not necessarily. And here's an example. So continuing with that remark, here's a counterexample. So suppose I have so x is a random variable that takes values 0, 1, and -1 with equal probability. And y is a random variable that takes 0 if x is not equal to 0. And it takes 1 if x is equal to 0. Clearly you can see that x and y are dependent, right? Not independent. So let's calculate the covariance of x and y. expected value of xy, when x, when x is, okay, so when x is not 0, y is 0, so xy will be 0. And when y is not 0, x is 0, so xy is always going to be 0. Right? Okay, so this term is always 0. What about expected value of x? Expected value of x is 1/3 0 plus 1/3 1 plus 1/3 -1, which is also 0. So no matter what the expected value of y is, so the covariance of this is 0, but are they independent? No. And if you want to check this, that x and y is not independent, let's look at the joint probability of 0 and 0. Can they, so this is just the probability of x equals 0 and y equals 0. So y equals 0 condition on x equals 0 times the probability that x equals 0. Can y be 0 if x is 0? No, if x is 0, y has to be 1, so this is 0. Okay. So this joint probability is 0. What is px of 0? That's just 1/3. Py of 0, that's just 2/3. Right? That's just the probability that x is not equal to 0. So x and y are not independent. So you have the covariance is 0, but they're not independent. So that's counterexample that's supporting this. And, maybe I'll talk about this next time.
Bless you.
I think he's allergic to probability. We should probably quit for today.
All right, okay, yeah, we're done for today. Do a couple more examples next class on expectation variance and covariance, and then start with moments of different